Hi, and welcome to this tutorial on how to model water quality using PySWMM and a new library called StormReactor. StormReactor allows you to model any pollutant treatment or generation process inside a SWM simulation. StormReactor now gives you the ability not only to model in nodes, for example, basins and storage volumes, but also in links like channels and conduits. And this new flexibility also allows you to do more things with real-time control as it relates to water quality. Real-time control is outside of the scope of today's tutorial. Today we'll just be focusing on modeling water quality inside a single node, which should be familiar to you if you have already worked with water quality treatment in SWM. All right, so let's get started. I want to start by referencing the Stormwater Water Quality Manual. Again, this is for EPA SWM. And if we go to page 94, we will see the example treatment expressions that they outline. These are like some of the most common water quality treatments that people model in EPA SWM. For example, event mean concentration, which is treatment that results in a constant concentration, constant removal treatment, treatment that results in a constant % removal, and there are 7 total of these. StormReactor provides the ability to model all of these sort of example treatment expressions in PySWM, but also a few others, but those are outside of today's scope. Today, we're going to focus specifically on event mean concentration. So the equation where we say C equals 10, for example. So the first thing we need to do is install StormReactor. I have my terminal open here. I'm working in a virtual environment called VirtEnv. That's sort of outside of the scope today, but it is good practice to use virtual environments. All right, so the first thing we need to do is install it, just like how we installed PySWM in a previous tutorial. So we will type pip install StormReactor, enter, and then you can see here it says successfully installed StormReactor version 1.2.0. All right, I'm going to type clear just to make our terminal a little easier to read. All right, so now we're ready to get started. And the first thing we need to do is to look at our input file. Okay, so our input file here is example1_waterquality.inp. We're going to open it up, and it's going to look like any other input file. But what we need to make sure is that treatment is enabled. So if we scroll down, we can see our pollutants. We have TSS and lead being modeled in this input file. And we needed to make sure that after pollutants, we see this section called treatment. And if you don't see it in one of your input files, you can simply copy and paste it from another one. So here I have enabled treatment in node 17. You can enable it in any of the nodes, but we want to make sure it's in the nodes that we want to model in, and today I picked 17. Let's pull up the picture of the example network so you can see what I'm talking about. So that's called example1.png. This is the same example network, like I said, from previous examples. So we can see it's actually the image from PySWMM that allows us to see the network really nicely. We can see here that node 17 is the one that we're looking at right here. Just put a little box around it. This is going to be the node we're going to run treatment in. And we're also going to be interested in node 24, which is the upstream node. We will refer to it as upstream node from now on. And then also node 18, which is the outfall. All right, so this is the part of the network we're going to focus on. But we could have focused on any other sections of the network, but we're going to keep it to that small section for simplicity today. So again, we see I initiated treatment in node 17. You have to say which pollutant. I picked TSS, and then there's that event mean concentration function from the input file, C equals 5. We can put this to any function. We just need something here for when StormReactor runs. Basically, StormReactor is going to kind of override the input file over and over again with whatever we set it to during the simulation. But we just need something to sort of enable treatment from the get-go. Input file looks good, and now we can get started. So we need a script in order to run our new model. So we're going to type touch water quality underscore writing.py. Okay, great. So now we can see it here in my browser here. We can see water quality underscore writing.py. And I added the underscore writing.py because we already have the full Python file here, but we're going to write it from scratch. So I'm going to double click it to open it. It opens in Sublime, which is my default program I use for writing Python. So the first thing we need to do is to import the libraries that we're interested in. So we need to say from PySWM import simulation. Now we need to also import StormReactor. So from StormReactor import water quality. Great. Now the next thing we need to do for StormReactor is to create what's called a configuration dictionary. So this is going to be a dictionary that allows us to tell StormReactor in which assets, right, in which nodes or links we want treatment to occur. And so it has a specific formulation. You can call it whatever, but I'm going to call it config here, equals. A dictionary has these little squiggly brackets. We need to tell it which node or link, what the name is from the input file. And again, we were focusing on node 17, if you remember, colon. And then we're going to basically make a dictionary of dictionaries. All right, so the next piece it needs in this dictionary is all the components it needs for 17 specifically. All right, so it needs to know what type it is, right? Because if we just say 17, it does not know if it is a node or a link. So we need to tell it that it's a node. And then we need to tell it what pollutant we're interested in. Okay, so pollutant, so we're TSS, just like we showed you in the input file. The next thing it needs to know is what treatment method, right? So what method within StormReactor are we interested in? And again, I showed you the 7 treatment methods that are provided by the SWM manual. There's also others that we provide in StormReactor, but today we're going to focus on event mean concentration. And so that looks like this, event mean concentration. And then the last thing we need are the parameters, right? So if you think about it, every water treatment method is a specific formula. Each formula has parameters that it needs in order to do what you want it to do. So specifically for parameters, it's another dictionary because some of the methods require 2, 3, 5 parameters. Event mean concentration is really simple. All it needs is C for what constant concentration you want it to set it to. And we're going to set it to 5. Okay, now I know you cannot see all of that, so let me make this a little bigger. Move this over, and let's also move our terminal down here. So, all right, so now we have our config dictionary. We tell it the name of the asset, that's 17, and we create a new dictionary with the inputs needed for StormReactor. What type is it, a node or a link? What pollutant are we interested in, TSS? Again, this could be lead, according to our input file. What method of treatment do we want to use? Here we're using event mean concentration, and then we need the parameters for that method. And in this case, we only need C, which is 5. There is a PDF file that has all of this information in this tutorial folder called waterquality.pdf. And in there, you'll see a list of those 7 treatment methods and the parameters that they need. So we should have everything compiled for you, so it's really simple to use. All right, so now that we have our configuration dictionary set, the next thing we need to do is to initialize the PySWM simulation. So it's exactly as we would do before with simulation. Our example 1 underscore water quality dot input as sim. Okay, and now we also need to initialize StormReactor's water quality module. So in that way you can set this to anything, but I usually set it WQ equals water quality. It takes 2 parameters, sim from PySWM, because it's going to use a bunch of PySWM's capabilities, and then the config. So now we need to tell it what to do each step of the simulation, just like you would with a traditional PySWM simulation. So we're going to go for step in sim, and then we're going to call WQ to call that water quality module that we just initiated, and put dot update WQ state. So what this will do is every time step, it's going to update water quality based on the configuration dictionary that we gave it. Control S to save my file, and now we can run it. Okay, so we're going to say Python. We need to call our water quality underscore writing.py, enter. And now we know that ran because, again, you get this sort of output from PySWM, but also we can see in our water quality folder up here, new report and output file. And now let's add a little more detail to this script so we can see a little bit more of what's actually happening behind the scenes. So the first thing we need to do is to also import the nodes class from PySWM. And now we're going to add some statements so that we can get some information from the simulation about our nodes and the pollutants that are being changed in the simulation. So we are going to say upstream node equals nodes sim, and then the name from the input file of the upstream node, which was 24, as we saw earlier. And again, you can call these anything you want. I'm trying to make the variables really descriptive so you can intuitively understand what's happening. Then let's call water quality node, our node that we're changing here with our configuration dictionary, nodes sim and 17. And then we're going to look at our outfall node, which was 18. So this is allowing us to use PySWM's functionality to get information about these three nodes whenever we want in the simulation. So now what we're going to do is every time step, we are going to print what the TSS concentration is in each of these three nodes, just so we can kind of see what's happening. So upstream node, okay, and then we're going to call upstream node dot, and this is the way you can get the pollutant concentration or quality in PySWM. Is essentially we initialized, right, node 24 up here, we called it upstream node. Now to access this, we call upstream node dot pollute underscore quality, and then we tell it which pollutant we are interested in here. Again, this could be lead if we were interested in lead. And if you wanted both, you could just leave it. If you wanted lead and TSS, we could remove that piece and just say pollutant quality, and it would give you the pollutant quality for every pollutant in that input file. All right, so now we want to do the other two nodes. We're going to save it, and now we will rerun. And now you'll see when we run this, a bunch of statements happening in our terminal. All right, so Python water quality underscore writing.py, and wow, you see all those prints. If we scroll up, we can see that for every time step, it was printing the concentration in each of these nodes. So what is actually happening here? So we can see that. Let's look at the very last time step. Okay, so I'll highlight these here. The upstream node at the last time step was around 4e to the negative 7 milligrams per liter. Obviously, that's very small. We can see then in the next node, in node 17, the water quality node, that we set the concentration to 5. And again, that's being called strictly from our config dictionary. And again, obviously, we wouldn't go most likely from 4e to the negative 7 to 5. This is just an illustrative example to show you that whatever you set it to in your Python script is what's going to be set in the simulation. And so again, this gives you immense freedom. Obviously, this example is not realistic, but just shows that flexibility. Okay, and then if we look at the outfall, we see that it's 4.98. So again, we have a little bit of a change, and that's because if you remember, I will open it really quickly, the network, we are changing the concentration in 17 to 5, but at 18 also gets flows directly from the subcatchment 8. I believe we're getting some additional flows from 8, which is sort of diluting that concentration at the outfall. So to me, this makes sense. So let's look really quickly at our report file. And so you'll see that it'll give you all of the same water quality reports, just as any other EPA SWM simulation would give you. All right, so let's go down and scroll and focus specifically on the water quality routing continuity. And I'm just going to screenshot this so we can look at it next step when we change the concentration again. We can see that TSS, we can see the inflow, the outflow, the flooding loss, etc. Okay, the other one I want us to look at is the outfall load. So we're going to need to scroll down a little bit. This outfall loading summary. And I'm going to screenshot this as well. And we will look at both of these after the next simulation. Okay, so now we're going to rerun this, but instead of running it with C equals 5, we're going to say C equals 50, just so we can see a little bit, see something different, and then compare the report files from the previous one and this one. On top of that, let's also make a figure. Let's see how these pollutants change with time. It's a little easier than the print statements, right? This is a little hard to digest, but if we make a figure, it'll be a lot more clear. So to do that, we first need to import a new library. Import matplotlib.pyplot as plot. So the next thing we need to do is to create some lists to store the data, because we need to store the concentrations every time step in order to actually make a figure. So what we're going to do is create 3 lists, call it upstream node underscore TSS. We hit equal, and these square brackets are how you create an empty list. Then we're going to go to water quality node underscore TSS equals square brackets, and then outfall node underscore TSS equals square brackets. So we're going to have one list for each of our nodes that we're interested in, okay? So now instead of printing these concentrations every time step, we are going to save these concentrations to these new lists. So to do that, we need to get rid of this print statement. And what we'll say is upstream node underscore TSS. That's the list name. And then for a list, we put dot append. And then we put the value inside those parentheses that we want to append to that list. So that's saying every step in the simulation, we want to get the upstream node TSS concentration and save it, append it to the list called upstream node underscore TSS. Now we're going to do that exact same thing for the other 3. So now our simulation is ready, but we need to actually give the script the text for creating the figure. So to do that, we need to call PLT. So we're going to say plt.plot. Now we call the list that has the TSS concentrations. We can tell it what kind of line we want it to plot as. So we're going to put a dotted line, which is the colon, and then we're going to label it so that we can create a legend and actually know exactly which node is which. We'll label it upstream node. We need to repeat that for our other 2. I'm going to use this as a solid line, which is just the dash. This time we will make it a dashed line. To make our figure have a little more information, we will also create an X label, right? So this is going to be our simulation across time. So our X label should be time. And then we will make a Y label, which we know is TSS, and we can even tell it what units, milligram per liter. We call plot.legend so that we can add a legend to the figure using the labels that we gave it above. And then the last line that we need is plot.show. And that's just going to allow us to show the figure at the end of the simulation. Save it. Again, so we call Python water quality underscore writing.py. We hit enter. And here you can see the figure. So a C, we see our time on the x-axis. We see TSS concentration on the y-axis. And then we have our legend here. We can see that the blue dashed line is the upstream node. The solid orange line is the water quality node. And then the dashed green line is our outfall. Well, we can see that at our upstream node, we have these peaks, right, that go over to a little over 100 milligram per liter, and then kind of fall back down between 20 and 40. then they go back to 0 during the dry periods of the simulation, and then they peak again during the next peak rainfall. And go back down again to 20, 40, and then go to 0. Okay, so that's based on the wash-off, build-up and wash-off equations that are in the input file, and obviously the input rain as well. Here we can see now the water quality node, which is the solid solid orange line, which is set to 50 for the entire simulation. And again, that's because that's what we set it to in our configuration dictionary. Again, this doesn't necessarily make sense, but this is a illustrative example of what we can do with StormReactor. So no matter what happens upstream, we have set it to be constant concentration of 50 milligrams per liter for the entire simulation. And then if we look at the outfall, which is the green line, we can see that we again have sort of like this peak at 100, then we hang out around 40 to 60, and then when it would probably drop back down to 0, we see it sit at 50 because, again, it uses the upstream information to know what it's doing downstream in SWM, right? And so here, the upstream node is the water quality node, which we've set to 50. And so this is impacting the downstream outfall concentration throughout the simulation. Again, we see another peak sort of at the end of this outfall. And again, that's from that rainfall and from, as I showed you in that figure earlier, the subcatchment 8, which also flows directly into the outfall without passing through the node 17 or the water quality node. So that's how you plot your water quality results from PySWMM and SWM and StormReactor. Now let's look at the report file. Okay, so I'm going to open this new report file. Okay, and then let's also pull open the screenshots from the simulation where we set the concentration equal to 5. I'll pull that up there. Let's open the outfall loading. So let's first look at the quality routing. We can see that the inflow is the same. We haven't changed the inflow as it relates to the wash-off, build-up and wash-off, right? Those are the same in both. The difference here is this external outflow. Now we can see that our outflow is 809 pounds of TSS, whereas before we only had 131 pounds of TSS. And that's again because we set that concentration in that one node to be 50 for the entire simulation. Again, this is new. As I was mentioning at the beginning, this is a new functionality in StormReactor. Before, you could only sort of reduce the concentration through the treatment functions, right? It was set in the SWM code that it can never increase. We changed that with StormReactor so that you can have a bit more flexibility. So now you can not only do treatment and reduce concentrations with time, but you can also increase concentrations with time, which is really important in stormwater networks if we think about erosion, for example. And that's sort of what I was thinking about when I made this example. We can sort of think of this node, let me pull up the picture again, this node 17 that we have set to be 5 or 50 constant concentration as maybe a node where erosion is happening constantly. Now, again, that is not realistic. We wouldn't have erosion 100% of the time. But again, we do have places where we have erosion and where we add pollutants to our network. And so this new ability allows you to not only do treatment, but also generation. So pollutant treatment and pollutant generation processes. And that's sort of illustrated in this example. Now, if we wanted to make this a bit more realistic, instead of just saying it's a constant concentration of erosion the entire simulation, we could set some sort of thresholds so that only above certain flows, then we have the erosion, for example. But that's beyond the scope of today's tutorial. Okay, so let's also check out this last piece of this output file, the outfall loading summary. So if we look down here, again, we have most of these things look the same. Let me pull this over so you can look directly above each other. The flow frequency percentage, the average flow CFS, that's all the same. The max flow is the same. Gallons are the same, but where we want to look at is this load. Total TSS load, again, 809, here 131. This, and the lead, again, hasn't changed. If we look, it's completely the same because we haven't touched lead in our simulation. We've only been focusing on TSS. All right, so I hope that convinces you that by controlling water quality with PySWMM and StormReactor, you can now run water quality just like you would in the Swim GUI, but now using Python, and that it actually gives you a lot more flexibility. We can now add pollutants, we can treat pollutants. You have all of the same treatment capabilities that you had in EPA Swim, but now more. And again, that extends to real-time control, which is outside of the scope of today's tutorial. All right, so I have included all of this information in this PDF. So in this PDF, you can see all of these steps. You'll see the code. You'll have some background on StormReactor, the entire code base that we use today, the output image to compare, some description of what's happening that I also dictated today. If you have any questions, we recommend that you post those on Stack Overflow and tag it with PySWMM. And again, like I mentioned at the beginning, I have added all 7 treatment methods at the end of this PDF. So amine concentration, constant removal, etc., and included the parameter that each of them needs. StormReactor has more than just these 7. You can do things like continuously stirred tank reactors, and a phosphorus model for bioretention systems that's also included in StormReactor. And it has the ability to create your own methods as well. And to learn more about that, you need to go to the StormReactor GitHub page, and there's a lot more information on how to use it and how to create your own methods. So with that, I'd really like to thank you for your time today. I hope this was helpful, and I hope you can see the potential for modeling water quality in PySWMM with StormReactor. And we hope that it becomes a resource and a tool that we all use and build upon, adding additional treatment methods to this library, expanding the abilities for so many to model all the complexities that are water quality processes and stormwater networks. Thank you, and I hope you have a great day.